now. So welcome everybody. So my name's Tom. I'm going to talk today about some traffic flow mathematics. So hopefully you'll forgive the pun, a crash course in the mathematics of traffic flow. But let me just maybe start by introducing myself. So that's me looking more professional than I look right now, wearing the glasses. Of course, got to appear intelligent at all times for headshots. But I'm from Indianapolis, Indiana, so I'm a fourth-year graduate student here at U of SC. So I earned my undergrad at Purdue University, and then I moved down here for grad school. So I work in the mathematics department partially as a graduate student, so I do some researching of things with my advisor. I came here, I did some classes, I passed a lot of exams. And now I'm pretty much just doing research with my advisor, and I also teach a class. So this semester I'm teaching Math 115. And let me just maybe get a poll. So are we all calculus students here, or some older students as well? Is that anyone past calculus? Okay, so you're a math major maybe?
Math major and computer science major.
Math and computer science, gotcha. Okay, and are you a junior, senior?
Senior.
Senior, nice, okay. So you've probably taken a class on differential equations and also on analysis. Okay, well, I'm not gonna try to talk super in detail about the nitty-gritty like analysis component of the talk, but what I wanna talk about is the following. So, before I get to that, I'll show you the pictures. Okay, there's gonna be lots of pictures in my talk today. So this one is, of course, you can see the cars moving forward, and what I want to highlight here is moving backwards, right? We see this interesting phenomenon happening, right? Where we have these vehicles bunching up, right? They're bunching up here, and then as time moves forward, the bunching, okay, is what is going to be propagating backwards throughout the highway, right? So even though everyone's moving in this direction, we have this interesting kind of bunching happening. And this is actually akin to what's going on in the ocean when we have a wave, right? It's a bunching of particles. Or if you have like a longitudinal wave, like I'm using my voice right now. So sound, what's happening is I'm compressing the airwaves, right? And we're having this wave which is being sent back. So we have all sorts of these different differential equations which help us to model these types of things. Particularly for fluid dynamics, which is going to be basically the heart of this talk, where what we're going to talk about is, well, how can we compare the motion of cars on the road to that of particles of water in a stream? So this is what we're going to be talking about. So for the outline of the talk, what I'm going to do, okay, so I understand that you're mostly calculus students, so we're going to have an introduction for partial differential equations that is not going to be too hardcore, I promise. I only have like 2 or 3 slides. So we're going to do a little bit of partial differential equations, and then what I'm going to do is go over a handful of different popular traffic models, and then we're going to get into the derivation of 1D scalar conservation law for traffic flow, which is kind of more in my vein of research. So, like I said, I'm not going to get super nitty-gritty with the analysis, but if you want to talk about it afterwards, then I'm happy to. So after I've introduced that, I'm going to talk about some of the problems that mathematicians face when modeling traffic flow using fluid dynamics. Okay, so the first thing I'm going to introduce is an ordinary differential equation. So are we all familiar with derivatives? Yeah? We've seen a derivative, we know how to do a derivative, maybe we learned the power rule and some other things. So what ordinary differential equations are, okay, is we are going to have an equation which relates a function to the derivatives of that function with respect to one variable. Okay, so I think probably everyone's familiar with seeing notation like what is in the box right now, right? So first derivative would be f prime, second derivative would be f double prime of x, right? So what do we have here? We have an equation relating functions, right? So a solution to an equation like this is not going to be a solution like the solution you might have for like a quadratic equation where you're going to get a certain number. Rather, for a differential equation, okay, the solution is going to be any function whose derivatives and the function itself satisfy the differential equation. Okay, so if you take an ODE class, you'll learn a lot about these. So here are some really simple ones written in 3 different notations. So we have the Leibniz notation, the Newton notation, okay? So maybe I'll dare to ask, if we take a look at this differential equation, okay, we have that the second derivative of the function, right, plus 2 times the first derivative would be equal to 3 times the function itself. Can anyone think of a function that might satisfy this kind of differential equation? Well, let me ask the following. Have any of you learned of a function f of x such that f of x is actually equal to its derivative? E to the x, right? So we've got e to the x, and moreover, what else would be true for e to the x? It's not just equal to its own derivative, but its derivative is also equal to its own derivative, which would be f double prime of x. Sorry for the bad writing here. So if we had a function which satisfied these 3 things, right, then it could satisfy this equation, right? Because what it says is this would be e to the x, right, plus 2e to the x equals 3e to the x, and that would be true, right? We'd be happy. So there's all sorts of different functions that might satisfy a differential equation. Typically, we need a little bit more information than just the differential equation in order to get a unique solution. But this is the basic idea behind differential equations. We want to come up with a function which satisfies the relationship here between its derivatives. Okay, so last comment I put on this slide is, okay, ODEs, especially ODEs which are nonlinear. Okay, I should explain what I mean by nonlinear. What I mean is that for a nonlinear, we might have also some products here, like y squared or something like this, okay? So if we add in something like that, things start to get really, 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 really hairy. And they're often either extremely difficult or maybe even impossible to solve explicitly. So people come up with all sorts of like approximations and things like that that they can use to solve them instead. Okay, so partial differential equations, okay, second to last differential equation slide, I think, are trickier. Okay, so partial, you might think, well, it's not as bad. It's only part of a differential equation, but actually it's worse. It's much, much worse. Because when we take partial differential equations, okay, we're going to relate the function not just to derivatives of itself, okay, but also to derivatives of itself with respect to different variables. So I use the del notation here. You can just imagine that those are d's for now. Just imagine that they're d's. Actually, it's pretty much always, well, I shouldn't ever say always, but you can think of them as d's. So we're basically taking what? The derivative of a function with respect to time is equal to some constant times the second derivative of that function with respect to space. Okay, so these are 2 famous, super famous partial differential equations. The first one is known as the heat equation, and the second one is known as the wave equation. Both of them for one-dimensional case. So we can also incorporate more spatial dimensions. So what differential equations do is they explain how something is changing both in time and in space. So if we do that, we can model a ton of different physical phenomena. So differential equations are basically the mathematical language of the physical world. We use them to describe things like the motion of the planets, or chemical reactions, or physics, or populations rising and falling, and so on and so forth. And they're even harder to solve, okay? In fact, there's vanishingly few partial differential equations which we can actually just go ahead and, it's gonna solve it. Most of the time, we're relegated to just kind of approximating techniques. Or maybe we can say as much as to say, there is a solution. And I don't know what it is, but I can say that there is one. Or something like this. Okay. So I just want to give an intuition for basically what these things are saying, okay? So I'm going to show you this and say that what does the heat equation really say? So if U is measuring the temperature of in like a steel rod, Okay, we have a steel rod. We're explaining what is the temperature at a given time and location, right? Then what we can say is, well, the way that the temperature is going to change over time is going to be related to the second derivative of the temperature in space. So what does that mean? Okay, well, the second derivative of the temperature in space, so you can imagine if this is our u down here, okay, then at location x equals 0, the temperature is currently what, 0.3 degrees or something like that, right? And the temperature a little bit further away is like less than that, right? So what does it mean if the derivative is positive? If the derivative with respect to time is positive, then the temperature is going to increase in time. Whereas if it is negative, then the temperature is going to decrease in time, as we can see in this animation. So what does the thing on the right have to do with all of this? Well, this is going to tell us the concavity or the convexity of our function, right? So here we have a function which is concave, right? It's concave or concave down. All right, so what does concavity really mean? Concavity means that at a point, I am roughly speaking larger than the average of my neighbors. Okay, so you can think of what might happen in a steel rod. If the middle is very hot, but the edges are quite cold, what's going to happen? The heat is going to flow from the center towards the edges, right? And we're going to equilibrate. Okay, so that's basic intuition for heat equation. That kind of intuition rarely gets you far in PD in my experience, but I hope you feel a little bit better now. Okay, so now I'm going to switch gears and talk a little bit about traffic models. So two of these traffic models involve differential equations. So the agent-based models are going to incorporate ODEs, and then conservation law, we're going to use PDEs. And the cellular automata model, we're not going to use either of those. So let's go with the simplest case first. We don't like differential equations. Let's stay away from them. So what do? Well, if we want to understand traffic models, well, first of all, why do we want to understand traffic models? Well, if we can explain mathematically what is happening on a roadway, then we can experiment mathematically with what happens to the model when we do various things. And if our model is a good model, that can help us to make predictions about what's going to happen on an actual roadway, right? So if we can do all of that, then we'll be happy. So what is the cellular automata? Well, we just say, well, there's just various grid spots on the road, okay? So these dots represent cars. And what we're going to say is, I'm not going to care about what an individual car is doing. I'm just going to say, what's happening in the cell? Is the cell filled or not filled? And then if it is filled, I'm going to come up with a rule for what is going to happen at the next stage. So I'll model maybe like in terms of seconds. So at second 1, it looks like this. What's going to happen at second 2 is going to be what I describe with a rule, right? So I might say, if there is a car in this cell and the following cell is empty, then at the next time step, this cell will become empty and this cell will become filled with the car. But what am I going to do when there's a car in front of me? I can't move forward because the cell is not empty, right? So we got to wait for this one to move forward. So what you can do is tell the computer, okay, do the rule like 1,000,000 times and see what happens. And you see interesting kinds of traffic jams forming or traffic behaviors, traffic waves moving back, and these sorts of things within this model. So it's really friendly for simulating using a computer. So let me show you a animation of that. So this is a 2D, 2D. This is, actually I guess it's 3D technically, because if you count the grayscale. But anyways, this is a 2D gas dynamics, okay? So what do we have? We have basically initially, let me restart it. Initially, we have a very high concentration of gas in one section. And what do gases want to do when they are in a space? They want to spread out and get away from the concentration of other gas particles. They're going to move each other away. So everyone who's here wants to go away, right? But what's going to happen next? Well, when they go away, they're going to form maybe another section of concentration over here. And then they're like, I'm too close to all my buddies. I got to get away. So they go away. right? And then you can use these types of cellular automata to kind of model what's going to happen, where you say, well, if my initial grid spot is next to a lot of other highly concentrated grid spots, then with some probability, maybe a high probability, I'm going to move away. And with a low probability, I'm going to stay where I am. And then you just let it go, and you get cool things like this. Okay, so the next model is the agent-based model. So rather than saying, okay, I'm going to say there's various grid spots, and the grid spots are either filled or they're not filled, and then we move according to like some kind of rule or something like that, we can just say, well, I'm just going to have a playground, and I'm going to have various different agents hanging out in the playground who are going to behave according to what they want to do. Okay, so how do we describe what a car wants to do? Well, we use a differential equation. Okay, so we use a second order differential equation. So if you've taken, you're all in Calc 1, right? Mostly Calc 1. Okay, so maybe you've learned about the position function, right? And maybe the derivative of the position function would be the velocity function, right? And what would I get if I took one more derivative, the second derivative of the position function? What would that tell me? Acceleration. Okay, A+. So we describe whether or not we're going to accelerate and how much by a function whose inputs are what? My current velocity, the velocity of the car in front of me, and also these two, my current position and the position of the car in front of me. So what do I care about? I care about how far away am I from the car in front of me? And I care about, well, am I driving a lot faster than they are, or am I driving a lot slower than they are? And that's going to tell me what? It's going to tell me whether I am stepping on the gas or if I'm stepping on the brake. Not that I use my left foot to do that. Okay. So this is the agent-based models. Okay. So again, you can just let these run, right? You just say, well, you accelerate according to your own will. Right? So you could say, maybe I'm going to accelerate or decelerate in order to maintain a certain following distance, right? If I get too close, then I'm like, stepping on the brake. Or maybe I just want to drive 90 miles an hour, so I'm going to drive as fast as I possibly can unless I'm inhibited by a car in front of me, or something like that. Okay. So, here's an animation of some, you can model this type of behavior of cells by agent-based models all the time, because what do the cells want to do? They want to eat food, right? So if there's food available nearby, then they might hang out and eat. But if there's lots of other dudes nearby eating up all the food, then maybe they're going to go somewhere else and try to eat the food somewhere else, right? So there's this battle between what they want and what they can get, right? And so you just have various agents, so you could say, well, let's put 1,000 yeast cells in here and see what they do. And you can try to model using something like that. Okay, so I'm going to talk now about the transition from what we call microscopic models, where we have individual cars on the road, to what we call macroscopic models, where we're not going to describe individual cars on the road, but we're going to describe rather the traffic density at a given point, okay? So I don't want you to think too hard about this picture, okay, because I'm committing a bit of sin here. But roughly speaking, okay, if this curve represented traffic density, then what does it say? It says, oh, there's not very many cars, and then there's a lot of cars very close together, and then the cars are sort of more spread out later on, right? So if I have a density function and I integrate, I get an area under the curve, such as this. Okay, maybe we haven't talked so much about integration yet. But there is a relationship between the area under this curve and the total traffic mass, which we would refer to as okay, if you take the discrete model and you say, well, in this grid space, I have 20 cars, and in this grid space, I have 18 cars, and in this grid space, I have however many cars, right? Then as you take this to the limit and you have basically a density function, then integrating under the curve would give you an area which would represent the area which you would have in this kind of box model, right? So if you get this kind of an area, then you can learn, well, how many cars are present from location 1 to location 2, which is a little bit different than saying I have predefined grid spots where there could be an amount of cars. Okay, so what we're going to describe going forward is the traffic density. So what we saw at the very start, right, with the animation was a wave of traffic density moving backwards, right? So you can imagine something like this moving to the left. If all of the cars are moving to the right, the wave of traffic density is moving backwards compared with the motion of the cars. Okay, so next up, I'm going to talk about conservation laws. So has anybody ever heard of conservation laws? Like conservation of mass, maybe? Conservation of, okay, yeah. So you might have learned about them in a physics class. So what do we basically say? We say, well, some quantity of something is never changing, right? So like, we have conservation of mass, which basically says unless we're blowing up atoms, the amount of mass in our system is not going to change unless you remove some, okay, or something like that. So that's what we're going to talk about for traffic flow because, of course, the amount of cars that we have is not going to change. We're not going to blip another car into existence or blip one out of existence. All right. So, okay, before we talk too much about conservation laws, I want to talk about the notion of a flux. So what is a flux? Well, you might have heard of like something is like we're having an influx of this or an outflux of that. What it means is it's going to describe the rate at which something is entering or exiting a system, right? So for us, it's going to be the rate at which cars are going, okay? And that's not going to depend just on how fast the cars are going, but also on what is the density of the cars. If we have a high density of cars moving very fast, then the flux will be huge, right? And if I have maybe just a couple of cars, but they're moving really fast, the flux would be comparatively smaller, right? So it depends not just on the density, but on the multiplication of the density with the velocity, u. So what do we get here? If you look at the units, what is density? Density is mass per unit length, right? And what is velocity? Velocity is length per unit time. If you multiply, what do we get? We cancel the length and we get mass per unit time. Okay, so it's describing the number of cars per second or cars per minute or something that pass through a given point at a given time. Okay, so this is basically a rate of change, okay? It's a rate of change. All right. So, okay, what I wanted to show here was, well, if you have tons of cars moving very fast, then the flux is very big. You could have maybe fewer cars, but still moving fast, then the flux is smaller. And then there's a question mark about whether it's bigger or not than a lot of cars moving with a slow speed. But of course, the worst case scenario would be we have very few cars moving very slow, right? So this is going to affect what is the value of the flux from basically this is the largest, this is the smallest, and these two in between, it's more of a question mark between which one is winning, how fast we're going versus how few cars there are. Okay, so what is the trick with traffic? Well, the trick with traffic is that, well, how fast I can drive depends on how dense the traffic is nearby. So if the traffic is very dense and it's very crowded on the roadway, then, well, I can't go very fast, right? So we write rho times u of rho to denote that u should be a function of rho because how fast I can go depends on how many cars are nearby. Okay, so this is going to lead into what we call continuity equations, which is the name that we give to partial differential equations which are derived from conservation laws. So I'm going to show you a quick derivation of how that works. Okay, so this is probably the most technical thing I'll do today. So what do we have? If we integrate a density, okay, then we will achieve, okay, the total mass. Okay, so this is like a mass per unit length multiplied with an infinitesimal length. So it's like a, well, I guess maybe you haven't done integration so much yet. But okay, you can imagine that if I were to take a mass and take the derivative of that mass, then what would that tell me? That would tell me the rate at which the mass is changing. Yes, the rate at which the mass is changing. Okay? So what is that going to be? Well, if I say I'm only interested in the total mass of cars from A to B, then what is going to be true? The rate of change of the mass, the total number of cars which are between A and B, okay, is going to be changing according to the rate at which they enter, okay, that's the flux at point A, minus the rate at which they are leaving, okay, minus the rate at which they are leaving. Okay, so what can we do now? What we can do is move everything over to this side. If we do this, then we have minus f of rho of TB, no, TA, and then plus f of rho of T, no, it's the other way around. No, it is that way, sorry. No, it is the other way around, Jesus, okay. So we have B, right? So what do we have? We have some function evaluated at the endpoints, okay, of this interval. So spoiler alert, there's this thing called the fundamental theorem of calculus. I don't know, they probably haven't learned that, have they? Okay, well, there is a fundamental theorem of calculus, which is essentially going to allow us to unintegrate this thing, okay, and express this difference as the integration of the derivative, okay? So when we do this, what do we obtain? What we obtain is the integral of some integrand is equal to 0 when we integrate this function from A to B. So loosely speaking, let's just, and I'm going to get in trouble with Rhonda for saying this, but let's just imagine that that the integral is representing nothing but the area under the curve. Okay, if the integral was representing nothing but the area under the curve, if the area under the curve is 0, and moreover, the endpoints A and B are arbitrary, right? The endpoints A and B are arbitrary, then what can we deduce? We can deduce that this integral is 0 for every single interval that we choose, which means that the integrand itself must be 0, which is how we obtain the differential equation seen below, which says rho t plus f of rho x. This means partial with respect to t, and this notation here means partial with respect to x. We obtain a differential equation which is relating the function rho with its derivatives of derivative in time and derivative in space. So yeah, let's not think too hard about how we got the differential equation, but now we have it, right? Now we have it, we can do something cool. Okay, so let's see what is the cool thing that we can do. Well, we can solve it, right? We can solve it. So what does this say in the end? It says that if our flux, okay, if our flux here is given by, remember, is given by rho times u, right? Is given by rho times u. Then what can we say if the velocity is a constant? That is what we're going to talk about next. Then what is going to happen is that this model is going to be reduced to something which we call linear advection. So linear advection is simply going to say all of the mass, okay, all of the mass is going to move through the space with a constant velocity. Okay, all of the mass is going to move through the space with a constant velocity. So we can solve this in the following way. Okay, hopefully this picture makes things a lot more clear, right? So the way this picture works, okay, is this here is our x-axis as normal, right? Here we have u, or our y-axis, as normal. But we introduce a third axis of time to represent how this function is going to change over time. So at time t equals 0, it looks like this, and after some time, everything has moved to the right a little bit. So at time t1 later on, the function looks like this. So this just looks like a wave moving through space, right? It's called a traveling wave because, well, it's a wave and it's traveling. So how do we figure out what is the height of the function going to be at some later time? The way we figure out what the height of the function is going to be at some later time is we say, well, I know how fast it's going and I know how long it has been. Right? So I'm just going to trace back along this line until I get back to the initial condition, and this will tell me what should the value of the function be at that other place in the spatial temporal plane, basically. Okay, so this is great. Everything works perfectly, right? Except what's not great about this in terms of traffic is that traffic doesn't really work like that, right? We know there's an ebb and a flow, and sometimes the traffic gets really bad or really sparse, right? So this isn't actually going to describe how our traffic works very well at all. What's way more realistic is not to say that, well, everyone on the road drives 60 miles an hour, no matter how close you are to who's in front of you. That's not very good. No, we're going to have something which says, well, if there's lots of cars nearby me, I'm going to drive slower, right? And so what is that going to produce? That is going to produce, okay, so these lines, which we can trace back upon to get the information later on, are going to intersect, okay, are going to intersect. So let me explain what's happening here. So time t equals 0, here is our initial distribution. So what is going to happen is that cars in the back, there's not very many cars nearby. They can drive very fast. Cars which are in front of them are driving very slow because there's lots of cars near them. So what's going to happen? Everyone's moving to the right, but the folks in this region are moving to the right very slowly, whereas the folks in this region, what are they doing? They're moving to the right very fast. Very fast. So fast, in fact, that they're going to catch up. Not only are they going to catch up to the people in front of them, that's going to cause the traffic density to increase even more, right? And when this happens, we end up with something like this, right? And this is very bad. Why is this bad? Well, you tell me, what is the derivative of this function at this point? Uh-oh. I don't know how to find the derivative of a function which isn't smooth, right? Or even continuous, for that matter, right? So this is where our model is going to completely break down. It becomes completely useless. So the problem that is happening, right, is that the derivative of our function is going to become minus infinity, right? Or it's going to become arbitrarily large to a point where we can't even actually compute it anymore, right? So this is what's happening, which is causing the breakdown of our model. So how are we going to avoid it? Well, okay, I should have used this slide first. What we're going to use is non-local information, right? So our traffic model, okay, only depends on the density where we are, right? But I can inform my driving sensibilities not just on what the cars next to me are doing, but also on what's going on the road 20 miles away, right? I can decide whether I'm going to take that route or whether I'm going to drive slower or what have you, right? So this is how we're going to try to address this problem. Make sure I'm staying on time. Okay, so this is our LWR model for traffic flow. So it stands for Lighthill, Witham, Richards, the people who created it. And what is the difference between this and the linear transport? The linear transport, we just take the traffic velocity to be a constant. Everyone's driving 60 miles an hour. What do I do for the LWR model? I say my velocity is going to be 1 minus the density of traffic, where traffic density is maximal at 1. So if traffic density is maximal, i.e. it's 1, so if rho is 1, what is this quantity going to be? 0, right? If we're at traffic jam density, I can't move an inch. However, if there's no traffic at all, right, then I can move with speed 1, the maximum speed that I can go. Okay, so this is how the traffic model works. The problem with it is you have the finite time shock formation for basically no matter what. Basically no matter what. So as long as our traffic has any point at which the traffic increases, then what's going to happen is the fast folks in the back are going to catch up with the slow folks in front, and we're going to get a traffic jam happening. Okay, so that's really bad because our model is useless because it doesn't work basically ever. So we can use this information to help make it work, and I'll show you how. We're going to say our velocity u is going to depend not only on the traffic density where I am, but also on this quantity q, which is going to be given by, I'm sorry, I'm doing a lot of integration for students who haven't seen integration yet. But again, this integral is an integral of the density. This is going to give us some traffic mass. And specifically, it's the integral from 0 to infinity. So if I take this integral, what it's actually going to tell me is exactly how many cars are ahead of me on the road, okay? So I'm just on a one-lane road. I want to know, are there 100 cars in front of me or 1,000 cars in front of me? And depending on how many cars are in front of me, it's also going to inform how fast I drive. I'm not just caring about, well, how close am I to the car in front of me and the car behind me. I'm also caring about how many cars are in front of me on the road. And if there's a lot of cars in front of me on the road, down the road, what do you think I'm going to do? Drive faster? Yeah, we should drive faster. No, we should drive slower, right? Okay, so that's what we're going to do. So how is that quantity q going to become involved here? We have e to the minus q. If q is large, what kind of number is e to the minus q? Small, right? So if there's lots of cars in front of me, I'm going to multiply my velocity by a small number. So that would make my velocity smaller. Whereas what's the largest number that this could be? If q is a positive number, what's the biggest number that this could be? Q has to be between 0 and infinity, right? Between 0 and infinity. When q becomes large, we already said this number is going to become very small, so we have a big effect. What if there's no cars in front of us? No cars at all means we do e to the 0, which is 1, which means our model just collapses to the local case. Okay, collapses to the local case. So this is going to help us. Basically, the idea is extremely simple. If there's lots of cars in front of me, I'm going to slow down preemptively. Okay, and we'll see what happens. Well, what happens is we get this theorem, which again, I'm not going to try to be super technical about this, but what does it say? It says essentially, using the non-local model, okay, using the non-local model, we can have increasing initial traffic profiles. It's possible that the traffic in front of me is increasing, which remember was the cause of the traffic jams before. However, when we use our new model, we have this extra slowdown term where we're going to slow down if there's lots of cars in front of us. We can prevent ourselves from catching up and causing the traffic jam, right? Okay, but the expense is, of course, we drive a little bit slower, but not as slow as we would drive if we came to a standstill for like an hour on the middle of the highway, right? Okay, so I guess what I want you to take away from this talk is not necessarily all of the details of this, but I hope you found something interesting about the different traffic models. You saw at the very least some pretty cool pictures and images, and this gives you some kind of a flavor of the things that people worry about when they're doing differential equations, right? There can be some very hairy things that can happen that can cause just total catastrophe for your model. And when that happens, you have to come up with very inventive solutions, inventive things to do to try to modify your model to prevent those bad things from happening. If you're successful, maybe it can even work in the real world. Okay, so that's all I have for today. So does anybody have any questions about that talk? Yeah.
Is this meant to be used for like self-driving vehicles?
Right. So exactly. What is okay, so what is encoded in this model, right, says that a driver is going to perfectly inform their driving based on the number of cars ahead, right? Which they can't really know unless you had something in the car that was telling them like, oh, there's lots of cars ahead, drive slower, right? Or more likely in the far future when we probably will have some kind of like traffic control system and all the self-driving cars are all talking to one another and there's this hive mind controller, then it can just set your speed for you, right? And you don't have to worry about it. So yes, it's more in the vein of like, this could be used maybe 100 or 200 or 300 years from now when we have like that sort of technology, right? But what mathematicians aren't interested in like actually doing it. They just want to know like how does the equation work, and it's interesting and in its own right. And you know, people study these things, and then the technological process happens quite a bit later.
But it could technically be used now. It would like, if you had like a system that just offered a suggestion to a driver of like it took data from like
Yeah.
Google Maps traffic or something.
Exactly. So, I mean, the problem with these models is they are so simplistic. They're so simplistic that literally we are driving on a one-lane, infinitely long road, right? That's what this model says. That's not very realistic. And for realistic, we have things like Google Maps which say, actually, get off at this exit, go somewhere else. Don't stay on this road, right? But yes, there are mechanisms wherein non-local information is used. One of the famous ones is the hive mind that they have in the Amazon factories, right? Where what they have is all these little robots on tracks, yes? And the robots are on the tracks and they want to go to various different boxes to get some kind of product and put it in a box and send it to your front door, right? But they all have to move together and avoid one another, right? And so there's like this hive mind that is controlling like, okay, well, you go here at this various speed and you go here at this various speed, and if we all do it perfectly, then nobody crosses each other. And it's also like perfectly efficient. So that's one case where it's already happening, actually. Does that answer your question?
Yeah.
Okay. Are there any other questions? Yeah.
For your gas model,
Mhm.
you had you call it Cellular, is that it?
Yeah.
Is that the 2D version of the slots, basically? For pixels?
Exactly, yeah, so that's what I was trying to show. So yes, exactly. So here we have slots, right? But you can imagine I have another row of slots here, right? I have another row of slots here. And then if there's like lots of people in the adjacent slots, okay, if there's lots of people nearby me, okay, like here, 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 and here, then I'm trying to move like away from all the other people. Does that make sense? So yeah, exactly. This is a two-dimensional version of the cellular automata. All right, any other questions? All right, cool. Then I'll close there. Thanks for your attention. And yeah, hope you have a good rest of your day.
So please be very careful as you head back to your dorms. Remember, it's dark outside. Walk in groups. Appreciate it. Hope to see you tomorrow. And if you didn't sign in, do you know if y'all got the sign in?
Yeah, thanks.